Welcome everybody in part 2 of section 7.3 of AP Chemistry series. Today we will cover a new topic, or the second part of the topic, which is the reaction quotient, and it's represented in terms of QC. I just want to recall the previous video. In the previous video, we covered the concept of Kc, and we said that it represents the equilibrium constant, and it's used at equilibrium for sure. So the concentrations of Kc are just like the concentration at the equilibrium of reaction. Today we're going to do the same thing, or almost the same thing, but the only difference between the concept of QC and Kc, or the QP and KP, or the QSP and KSP. The only difference is the Ks are calculated at equilibrium, so we use the equilibrium concentrations. For the QCs or QPs or QSPs, actually they're used at non-equilibrium thing. For example, you can use them at the initial times of the reaction. So how can I calculate them? What do they represent? What is the purpose of calculating the QC and KC? The first thing that you have to keep in mind, the value of the QC has the same expression as KC. You can see that this equation here, we have some products and some reactants. If we want to calculate the QC, you have to put the products over reactants. And don't forget the coefficients represent their powers. We put them in square bracket. It's almost the same thing as the Kc, okay? But it's done at non-equilibrium thing. But the question now, what does the Q tell us? The reaction quotient QC describes the relative concentrations of reaction species at any time. So we have 3 rules for that, and now let's cover each one apart. Rule number 1 says if the value of Q and K are equal to each other, then we can say the reaction or the system is at equilibrium. Okay. Second case says if Q is greater than K. Okay. I won't explain this process in terms of this relationship. Let's go back again in here. If Q is greater than K, it means you have so many products that are greater than reactant. At the end, your reaction wants to be in equilibrium in which Q must be equal to the value of K. And since you have more products at that point in which you have a Q greater than K, the reaction needs to decrease the amount of the products, okay, by shifting to form more reactants and consume more products. So our target, in order to make them equal, the amount of the product must decrease. How does it decrease? By shifting the reaction to form more reactants. The amount of the products start to decrease to form more reactants. So the product decreases and the reactant concentration will increase. Okay, so let's go back again and read this paragraph down below. It says, the concentration of a product is too large and that of reactant too small. Substances on the right side of a chemical equation react to form more substances on the left side. The reaction proceeds from right to left to approach equilibrium. You have to keep in mind there's a beautiful point that you have to keep in mind. Do not use, let's say, left and right in your expressions, or let's say if you want to describe the direction of reaction. Instead of that, you have to say the reaction will be shifted to form more reactants or shifting to form more products. It's precise. And finally, let's hit on the third point at which the Q is less than K. If the Q is less than K, it means you have, since the ratio represents the products of reactants and it's a very small value at that point, and it means that you have so many reactants, but you have a little amount of product. And at the end, the reaction has to be in equilibrium in which Q becomes equal to the value of K. So how can I decrease the amount of reactants? Decreasing the amount of reactants by shifting the reaction to form more products and decreasing the amount of reactant. So the reactant at that point will, like the concentration of reactant will decrease, whereas the concentration of a product will increase. At that point, this process happens until we reach to the target of VQ becomes equal to K, which is the process that is done at equilibrium. Now let's go just like to read the paragraph again. The concentration of a product is too small and the reactants too large. The reaction, in order to, you can see, to achieve equilibrium by forming more products, you have to say it proceeds from reactants, not to right, to form more products. Okay, now let's take a real example in how to calculate it. Well, look at this beautiful reaction. Okay, we are given a piece of a reaction with its corresponding value of Kc. You can see that the value of Kc is less than 1, which tells me that we have so far, reaction is favored to form more reactants, not products, but it's not the case so far. Now the question says, if the initial concentration of the products and reactants that are given to us, is the system at equilibrium? If not, which way will reaction shift? Left to right. We don't say left to right, we say like to products or reactants. Please don't use these two words in your AP exams. It's not allowed. Okay, since the value of Kc is given to me, and the question is talking about initial values, so we can calculate the QC from initial. As we mentioned before, the QC is used to calculate the concentration ratios at non-equilibrium thing. So I have to say, okay, QC has an expression, which is the products. Make sure that all of these guys are gaseous or aqueous. So we can say, okay, I have the concentration of NO to the power 2 multiplied by the concentration of Cl2 over the concentration of NoCl to the power 2. And then we have to substitute the values. What's the concentration of NO? It's 0.75 to the power 2 multiplied by the concentration of Cl, which is 0.05, and then it's divided by the concentration of NaCl, which is 0.15 squared. And now the answer is 1.25. Now, the value of QC is equal to 1.25, and the given value of Kc is equal to 1.2 times 10 to the power -3. Now, what's the relationship between the two guys in here? You can see that the QC is greater than the Kc. So at that point, since the QC is greater, then we have so many products. Okay. In order to decrease the products, the reaction has to shift to the reactant side. So we can say that it's not at equilibrium. Okay. And however, the reaction, okay, has to shift from products to form more reactants, okay, to reach equilibrium. Okay, the QC is greater than Kc. It means that you have so many products that are greater than reactants. In order to make the QC same as the Kc, the product must decrease. How does it decrease? By shifting to form more reactants. Shifting more reactants leads to decrease the products and increasing the reactants. Now let's solve the next question and see it's the same idea. The value of Kc is given for a corresponding reaction. Make sure that all of the guys are in aqueous or in gaseous. It's aqueous. No, we don't consider water since it's a pure liquid, and NH3. Now the QC is equal to, it is the expression of OH negative, okay, multiplied by the concentration of NH4, which is ammonium, divided by the concentration of NH3, and we don't use water for sure. And then what is the concentration of OH negative? It's 0.0025. It's multiplied by the concentration of NH4, which is also 0.0025, and then you divide it over the concentration of NH3, which is 0.5. So the answer is equal to 0.000125. Technically, if you want to change it in terms of these words, you can say this is 1, 2, 3, 4, 5. So we can say it's 1.25 times 10 to the power negative 5. Now, what is the relationship? This is the QC, and the KC is equal to 1.8 times 10 to the power negative 5. Then you can notice that the QC is less than the value of KC. So if the value of a QC is less than KC, it means you have so many reactants that are greater than a product. In order to make the reaction to on a value of Q same as K, the reaction has to decrease the amount of reactants by shifting to four more products. So the reaction will shift from reactants to form more products. Okay, so the concentration of reactants will decrease and the product will increase until the reaction reaches to the equilibrium in which the value of Q becomes the same as the value of K.